Prove each of the statements in 10 through 18 by mathematical induction. This is the summation from I equals 1 to n minus 1 of I times I plus 1 equals n times n minus 1 times n plus 1 all over 3 for every integer n greater than or equal to 2. So the first thing we need to do is we need to identify what our statement P of n is. Keep in mind that P of n has to be a statement in terms of n, but can't include any quantification. So this right here is my P of n. P of n is a statement about equality, which says that the left-hand side here equals the right-hand side. So let's prove that this is true for every integer n greater than or equal to 2. Let's start with the base case. This is the smallest integer n such that P of n is true, which in this case corresponds to n equals 2. So let's see what it is that we need to show. We need to show that the summation from I equals 1, 2 minus 1, which is the n minus 1, in this case n is 2. I is our index variable, so we're just going to leave I by itself. And then on the right-hand side, we're going to replace n with 2. So this is the thing that we need to show, which is why I put a question mark here, because if we want to show that this is true, we can't simply assert it on line 1. We have to establish why these two things are actually equal to each other. And the way we can do that is we can evaluate the left-hand side and the right-hand side separately and see if we get the same outcome. So let's take a look at the left-hand side. So the index variable I varies from 1 to 2 minus 1, which is 1. So this summation is a summation with only one term. Specifically, the index variable varies from I equals 1 to I equals 1, meaning that I does not increment. The only term in the summation corresponds to when I equals 1. There is no I equals 2 or I equals 3. It's just I equals 1 and that's it. So if we plug in I equals 1, we get 1 times 1 plus 1. And that's the only term in the series, which is 1 times 2. And that's 2. So the left-hand side of this equation is 2. The right-hand side is 2 times 1 times 3, all over 3, which is 2. So because 2 equals 2, we can say that the left-hand side of P of 2 is the same as the right-hand side of P of 2. So that's the base case. Now let's get to the inductive step. So we're going to let k be an arbitrary integer with k greater than or equal to 2. And we're going to assume that P of k is true. So the first thing we should do is we should explain what that means. What is P of k? Well, P of k is the same as the statement P of n, but we replace all the n's with k's. That means we leave our index variable I alone, but our upper bound is going to change to k minus 1. And we're going to do the same to the right-hand side where we replace all of the n's with k's. So this means that this equality is true. We get to assume that this is true. So we want to show that P of k plus 1 is true. Now, before we move on, let's try to get a clearer picture of what our goal here is by writing out what P of k plus 1 is. So P of k plus 1 is the summation from I equals 1 to k plus 1 minus 1, which is just k. And then we leave the index variable I alone. And then on the right-hand side, we replace n with k plus 1, which would be k plus 1 times k plus 1 minus 1, which is just k, and then times k plus 1, which is k plus 2. And this is all over 3. So this is the goal. Now, before I move on, I want to explain a little bit more about these two equalities, because if you notice, this might be a little confusing. I have two equal symbols here, and in this context, both equal symbols actually represent different things. So for you programmers out there, this second equal symbol is more like a double equal symbol, meaning that the output of this operation is either true or false. So P of k plus 1 is defined as either a true or a false statement. So the output of this operation is either true or false. And this equal symbol, the first equal symbol, is an equal symbol, but by definition, meaning that we're defining what P of k plus 1 is according to the formula for P of n. We're just replacing n with k plus 1. So the first equal symbol is more like instantiating what P of k plus 1 is, and the second equal symbol is more like an operation to check if the left-hand side equals the right-hand side, and the output of that operation is either true or false, meaning that P of k plus 1 is defined to be either true or false. And in this context, we want to show that this is true. So what exactly do we want to show that's true? We want to show that the left-hand side of P of k plus 1 is equal to the right-hand side of P of k plus 1. So we're going to start with one of these sides, and we're going to manipulate it to look like the other side. That's how we prove the inductive step. So what I'm going to do is I'm going to take the left-hand side. And if you watch the previous video, you can see why it is that I picked this left-hand side rather than the right-hand side. It's because it's a summation here. So what I'm going to do is I'm going to say that the left-hand side of P of k plus 1 is this summation from I equals 1 to k of I times I plus 1. Now, in mathematical induction proofs, whenever you have a product or a series, the strategy is usually to take out one or two of the terms, depending on how complicated this induction proof is. In this case, we're going to pull off the last term. And the reason is because if we take out the last term of the series, we'll end up isolating a new series that varies, that can be represented with an index variable that varies from I equals 1 to k minus 1 instead of I equals 1 to k. So the first thing I'm going to do is I'm going to rewrite this summation in expanded form. And this is a very common strategy to do, which means I'm going to write out the terms. So the first term corresponds to when I equals 1. So I'm going to plug in I equals 1. That's 1 times 2. And then the next term is when I equals 2. So that's 2 times 2 plus 1, which is 3. And then I equals 3 would be 3 times 4. And then we keep going all the way up to, I'm going to write out the last two terms. So we have to think about the second to last term. The last term corresponds to when I equals k. So the second to last term would correspond to when I equals k minus 1. So I'm going to plug in k minus 1 into my formula here, which would be k minus 1 times k minus 1 plus 1, which is just k. That's the second to last term. And again, that's me plugging in k minus 1 into I in this formula. That's how I get k minus 1 times k minus 1 plus 1, which is k. That's the second to last term. Then the last term corresponds to when I equals k, which is k times k plus 1. So this is the expanded form of that summation. The trick here is that if I isolate this summation using the first k minus 1 terms, then I can use my inductive step. The goal with mathematical induction is to utilize your inductive step. If you don't utilize your inductive step, then you're not using mathematical induction correct. So now I'm going to rewrite this series back into summation notation. This is equal to the summation from I equals 1 to k minus 1 of I times I plus 1. So that's the first k minus 1 terms, and then the last term that we pulled out is this k times k plus 1. So now we can use our inductive hypothesis because this summation right here is the left-hand side of P of k, and we get to assume that P of k is true. We assumed that P of k is true up here, which means that this summation is equal to this specific fraction. And so I'm going to replace this summation with that fraction here. So this is equal to, instead of the summation, I'm just going to write k times k minus 1 times k plus 1 all over 3. And then we still have this term here, k times k plus 1. Now, when we do this substitution, it's important to note on the side here that this is true by the inductive hypothesis. You have to reference somewhere in your proof explicitly by, I put capital I, capital H, to say by the inductive hypothesis. If you don't say by the inductive hypothesis in your proof, then it's unclear as to why these two things are true. Then it's unclear as to why these two things are equal to each other. So next we need to show that this equals the right-hand side of P of k plus 1. We started with the left-hand side of P of k plus 1, and we showed that this equals the summation, which equals this summation, which equals this summation, which equals this. Eventually, we want to show that this equals the right-hand side of P of k plus 1, because then that would mean that P of k plus 1 is true. And that's our goal, is to show that P of k plus 1 is true. So the next thing we need to do is we need to simplify this expression to make it look like the right-hand side of P of k plus 1. The way I'm going to do that is I'm going to distribute k minus 1 times k plus 1. I'm also going to rewrite this term with a denominator of 3 so that I can combine fractions. So all I'm doing here is some algebra. K minus 1 times k plus 1 is k squared minus 1 all over 3. And then for the second term, I'm going to rewrite this as 3 times k plus 1 all over 3. This way, now we have a common denominator and we can combine fractions. But before we do that, I'm also going to distribute these factors here. So I'm distributing and combining here. This is going to be k cubed minus k plus 3k squared plus 3k all over 3. We can combine like terms to rewrite this as k cubed plus 3k squared. And then minus k plus 3k is a total of plus 2k all over 3. Next, I'm going to try to simplify this numerator by factoring again. It kind of seems backwards because we just distributed everything and now we're factoring again. So we're expanding and then we're compressing. But if we factor out a k, we can write this as k times k squared plus 3k plus 2 all over 3. And then lastly, we can factor k squared plus 3k plus 2 as k plus 2 times k plus 1. So this is k times k plus 1 times k plus 2 all over 3. And this is the right-hand side of p of k plus 1. And so that means that the left-hand side of p of k plus 1 equals the right-hand side of p of k plus 1, which means that p of k plus 1 is true. But what did we assume to get here? We assumed explicitly the inductive step, which is p of k. So the truth of p of k implies the truth of p of k plus 1 logically, and this is the inductive step. From here we can say, by mathematical induction, the statement p of n is true for all n greater than or equal to 2. And that's the end of this proof by mathematical induction. Thanks everyone, and I'll see you in the next video.